Okay, so another example based on the same problem. So based on the same system, there is yet another solution which is available in this Word file. So I'm not going to go over this example, but this is the same system with just different parameter values. So these are the parameters. So if you look at the solution, you again have some complex poles, and for this complex pole you can solve it by using complex residues, or you can keep that as a second order term and calculate A and B values manually, and from there you can take the inverse of this second order term by making it look like the sine and cosine terms in the Laplace table. Okay, so this is the cosine term and this is the sine term, and in the end you get the inverse in this form. Okay, so I will going to give you this file as well. So this will be posted on the forum. Okay, so there will be some application of this concept. Okay, but let me show you one question from the previous exams, which so I think this is an interesting question. This is the second question from 2 years ago. So in this question, I gave the time response as a function in time domain. So this is what I gave directly. And so this is given as the unit step response. So I think so. It's not explicitly stated here, but this is the response when the initial conditions were 0 and the input was a unit step function. So from here, I ask you to calculate the response to the unit step function, but this time with these initial conditions instead of 0 initial conditions. So this is, I think, this is an interesting question. So first, you start from here. So you look at these terms and you go back to S domain. In fact, the solution is given for this problem already. So you take the inverse approach. Okay, so you start from time domain, go back to Laplace domain, and then combining these terms together, you get the Y expression in S domain as this. So this was given to be the unit step response. So this S should be due to the input function. So the transfer function is obtained directly. So this is the transfer function. To calculate the response with initial conditions and input function, you from here you go back to the time domain. Okay, so this is the S domain expression. So you write it in this form. So you write it as S square plus or S plus 13 times phi of S is equal to minus S plus 13. Benim yazım eskiden bir tık daha güzelmiş sanki. Giderek kötüleşiyor. Zaten zamanla insanlar bu yeteneğini kaybedecekler diye bir endişem var benim. Ya ben kaybediyorum en azından. Şimdi benim o hep oğlumdan da bahsediyorum son zamanlarda. Ödevlerini o da şimdi alıştı. PDF'de falan yazıyor. Oğlum diyorum, sen yazı yazmayı öğreniyorsun yani. Senin burada elle yazman bekleniyor. Onunla tabii kolayına geliyor şey yapmak, type etmek. Şimdi el yazısı öğreniyorlar. Milli Eğitim Bakanlığı bu el yazısı fontunu da koymuş internete. Onu indirince gayet güzel el yazısıyla yazılabiliyor Word'de falan. So anyway, so from here you take the inverse transform. So we know that this is y double dot. This is 4y dot and this is 13y. So you go back all the way to the original differential equation of the system. So this is the original differential equation of the system, and then from there you start once again taking all the Laplace transformations, but this time you include the initial conditions while taking Laplace transformation. Okay, so these are the additional terms you get due to the initial conditions, and this one. So from there you obtain this expression and then take the inverse of that, and the inverse. So this is the solution to that problem. So that's an interesting problem. So okay, now let's take a step back and okay, so this is the system which we started talking about at the very first lecture of this course. There's an input, system itself, and the output due to that input. So this is a signal in time domain. The output is another signal in time domain. And for this system, we have some equations, right? For dynamic system, these are differential equations. So when taking Laplace transform, this becomes a signal in S domain, capital F. And these differential equations turn into some algebraic equations. Then we call this the transfer function. So calculating the response is just multiplication of the transfer function with the input function. And then from here we go back to time domain. So the transfer function of a linear time invariant system is defined as the ratio of Laplace transform of the output to the Laplace transform of the input, with the assumption that all initial conditions are 0. So if you have multiple inputs and multiple outputs in a system, then this is not that easy. Okay, so let's take a look at that case for a moment. Okay, so imagine a system with more than one input and more than one output. Okay, so in the general case, let's say there are p number of inputs, u1 up to up, and q number of outputs, y1 to yq. So if there's just one input and one output, we said that transfer function is equal to the ratio of output to input. But this time we have many inputs and many outputs, right? And let's assume that this is still a linear system, linear dynamic system. So what we do for such systems is the following. So we consider each of these inputs and outputs separately. Okay, so for example, first we consider the first input only, and then set all the remaining inputs to 0. So let's say we say U2 up to UP are all equal to 0. So we have just one input exciting the system. Then all these Q outputs will be affected by this one input. Okay, so this Y1 will be affected due to U1. Y2 will be affected because of U1, and similarly all the outputs will be affected. And for each of these outputs that are changed due to the first input, we can write similar relations in S domain. Okay, so we can say that Y1 is equal to some transfer function times U1. Y2 is equal to some other transfer function times U1. So this can be done for all Q outputs. So we have Q number of such relations. And remember, these are still due to the first input changing the system, right? So that's why we denote these Y11, Y21, YQ1. So this one means that this is the changes are due to the first input. So we repeat this for all the other inputs. So as the second step, in first step U1 was non-zero, but everything else was 0. In second step, we assume that U2 is non-zero, but all the other inputs are 0. And for this case, we have Q more equalities like that. The second input this time affecting all the outputs, and we call this Y12 up to YQ2. And if you want to know what happens when you apply all P inputs at the same time, you calculate the outputs due to all inputs separately and then add them together. So this is again possible because of the linearity of the system. So for example, if you are looking at the first output, if you give U1 to the first input channel, this is what you see in the output. If you apply U2 to the the first input channel again, to the second input channel, this is what you observe in the first output. And if you add all them together, the overall result you will see in the first output will be the sum of all these individual outputs. Okay, so this is the result output you see at first output when you give the first input. The result in the first output when you give the second input, and this is the result you observe in the first output when you give input to the P channel number P. Okay, so you add them all together. So this summation on the right hand side, you add all these things. You add this term plus this term plus all the terms for the remaining inputs, which are written here. And this can be written in a matrix form. Okay, U1 times this transfer function, U2 times this, and this can be written in this form: a row matrix multiplied with this column matrix. The result is a scalar, which is Y1. And you do this for the other outputs as well. For the second output, you write a similar expression. But remember, these are all different transfer functions. Okay? And in the end, you get this relation in matrix form. On the right hand side, you have P inputs instead of a single input we saw before. And on the left hand side, you have Q outputs instead of a single output. But in the middle, you have this huge matrix. And this matrix is such that every element in this matrix itself is a transfer function. Okay, so you have a matrix of transfer functions. Okay, so there's an example. So this is probably one of the systems we saw before. So this could be the car suspension or just a system with two meshes. So I think it's the car suspension example. Anyway. We have one input, so Q is equal to 1, and so P is equal to 1, and two outputs, right? So the Q is equal to 2. So according to here, for this system, we should be so there are two outputs, and this should be equal to so the transfer function matrix for this problem should be should have two rows and one column, and we can obtain these transfer functions at one step using the equations. So let's take a look at the equations now. So we have two differential equations, and we have, so this is not very clear, but you can see that this is y1 and y2. These are y1, y2. And then you have derivatives of y1 and y2. And the input is here. So this is the inputs you're giving to the system. So you start taking the Laplace transformation of these equations, and if you have, since we are looking for the transfer function, just remember that for finding the transfer function, you always assume zero initial conditions. You may have initial conditions in your system. In this case, you can use the initial conditions, and then you can find the response through that. But you shouldn't call the function you obtain in the end that includes initial conditions as the transfer function. Okay, just remember that. So we assume initial conditions are equal to 0 and take the Laplace transformation of these two equations. So you have two equations, and these two equations involve y1 and y2. And you can write the Laplace transformation of these two equations directly in matrix form. So you collect y1 and y2 terms together and then write them in the matrix form. Okay, so you should just take a look at these two equations and then see that these two equations are written here. So these just the same equations written in matrix form. So this is what you're trying to obtain, right? You're trying to obtain, leave y1 and y2 alone to obtain the transfer function matrix. So this is a step close to that, but not quite what we were looking for, because here y1 and y2 are not alone. Okay, so still y1 and y2 are multiplied with this matrix of S. So to obtain what we were looking for, we need to somehow take this term to the other side of the equation, and that is done by using matrix inverses, right? So if you call this A of S, this is Y of S, and this is B of S. So this is what you have. If you find the inverse of this matrix A of S and multiply this equation from the left hand side with the inverse, so A inverse times A will be identity, which will leave Y of S alone. And on the right hand side, you will have A inverse times B times F. So y of s and y of s is this column vector. So this is the transfer function matrix we were looking for. And to find that, this is the matrix we need to take the inverse of. So you can just treat it as a regular 2 by 2 matrix. So, and if you know how to take the inverse of a 2 by 2 matrix, that you can apply that directly here. So in fact, this is how you do it, right? If this is your 2 by 2 matrix, taking the inverse is the following. You first find the determinant of this matrix. The inverse is 1 over determinant times you arrange these terms a little bit, right? So you switch the places of this term with this term. So A22 comes in here and A11 goes there. And then you make, you use the negative of these off-diagonal terms, right? This is negative of this and this is negative of that. And these A11 and A22, they are all shown here. So these are the elements of your matrix. And in the end, the transfer function matrix can be calculated from here. Okay? Mm-hmm. Output'u mu? Output'u bilmiyoruz aslında, yani input'u biliyoruz ama.
Yani transfer fonksiyonu
Hı hı.
fonksiyonları daha önce buldum. Onları kullandım. Yani şimdi kafam değişti. Output'u biliyoruz yani.
Ya output'u şöyle biliyoruz. Sistemin output'u şudur diye bize söylenmiş.
Söylenmiş. Tamam. Oradan transfer fonksiyona geçmek.
Hı hı. Ama şurada şöyle bir trik var. Ya bu sınavda böyle multi input'lu multi output'lu bir soru sorabilirim. Şimdi output'lar bizim seçtiğimiz bir şey aslında. Yani sistemin output'unu biz farklı bir şey seçebiliriz. Şimdi burada y1 ve y2 olarak verilmiş ve bunlarla ilgili denklemler de elimizde. Ve biz buradan şeyi çıkardık. Transfer fonksiyon matrisi çıktı. So let me continue in English. So output is something we choose depending on our purposes. So for this example, I could have defined the output as follows. Instead of bundan da güzel sınav sorusu olur aslında ya. Şuraya yazayım, oradan kalanında sınavda şey yaparım. Outputs of a system chosen among the variables in the system depending on our needs. The above example is for spring mass damper system with two masses, and the outputs are chosen and two outputs are chosen as the positions of the masses. So let me just draw the figure for that. So this is, let's say, y1 and this, let's say, y2. instead of that, we could have defined just one output as the distance between the blocks.
Bir şey yani. Şimdi bu sistemimizde biz outputları bilmiyoruz ama outputları nasıl represent ettiğimizi biliyoruz matematik modeller. Bununla birlikte de aslında şey olması gerekiyor. Yani bir given input için biz bu denklemlerden çevirdiğimiz transfer fonksiyonuna nasıl bir output çıkacağını görüyoruz. Sonuç olarak.
Evet. So if you define your output as the distance between the blocks, then you can define this new output in terms of the two outputs that were defined previously, which are y1 minus y2, right? So if this is how you define your new output, so now the system turned into a single input, single output system, right? So now we have just one input as before. And now the output is just one variable, which is the distance between the two blocks, right? So the previously system had two outputs. Now it's the same system, so the physics of the system didn't change, but the output is defined as just single term. So if I ask you to find the transfer function for this new output, so let me call this G new S times f of S. We can calculate this new transfer function if we know the two transfer functions corresponding to the previous two inputs, right? So suppose that these were calculated before. And I know that the new output is nothing but this difference between the two previously defined outputs. So the new y is equal to y1 minus y2. So I can write that as y1s is equal to g11s times f of s, but y2s is g21s times f of s. So I can take f of s out of the parentheses, and that gives me g11s minus g21s times f of s. And now this difference is the new transfer function I was looking for. Okay, so let me call this G new. So when there were two outputs defined, there were two transfer functions, and the transfer function was a matrix in this form. But when I define just one output, and for one output there should be one transfer function, and this one transfer function can be obtained in terms of the previous two transfer functions, as you see here.
İki tane output olan function'da input olarak f2 iki şey var.
Yok, bir tane. So there's one input here. So we just apply a single force to one of the masses. So there's one input. Or we could have defined the output as the speed of the second block, for example. In which case the output is y2 dot, for example. And if I take the Laplace transformation of that, y of s is equal to the Laplace transform of y2 dot is s times capital Y2 of s, right? But I can write the capital Y2 of s, so this is Y2 of s. And this is a new transfer function for the new outputs of Y2 dot. Okay. So I'm planning on giving, asking a question with multiple inputs and multiple outputs, but so I should really be careful because things can get very messy very easily. So even though the procedure is really simple, but if you go back to this previous example, you need to obtain this transfer function. You need to, where's my A of S matrix? So you need to take the inverse of a 2 by 2 matrix, right? And this involves this procedure, and so the transfer functions can get very crowded, and I don't want you to be buried with such crowded terms. So I'm going to design questions carefully, but if I can find a simple question that involves multiple inputs and outputs, then I'm thinking on asking that. Okay. And there should be a question with 2 inputs or 2 outputs in the previous exams, right? So I don't know. I didn't look at all the questions carefully, but let's. Okay, so if you look at this second question from the last year's midterm, so there are 2 outputs here. So this is the same problem actually. So you have 1 input, but the 2 inputs are defined like that. The only difference is this second block is given to be massless, and the solution should be available here. Şu 3. soru çok straightforward olmuş. Ona bakıyorum burada bir. So this is a very straightforward question. The transfer function is given, and you have to find the output if the input applies the unit step function. The initial conditions are 0. So this is just a direct application of finding the inverse Laplace transform with partial fraction expansion. Efendim? Evet, yani bu işte bu sınavda yok ya. Burası boş çıkmış bu arada. Neyse orada herhalde artık yorgunluğuma gelmiş yani. Aslında doğru tabii ya, sınav hazırlamak hakikaten zor bir iş yani. Bütün sınıfın dağılımını görmek önemli. Yani az bilen de az bildiğini ne kadar biliyorsa ortaya çıksın. Yani şimdi çok böyle detaylı, hep böyle bir şeyi olan, ne derler, görülmesi gereken özel bir noktası olan sorularda oluşturursan sınavda ortalama bir öğrenci hiçbirini göremezse direkt sıfır alır çıkar. Ama o az bilen öğrencinin de az bildiğini görmek açısından aslında bütün soruları koymak lazım. Ya da hepsi böyle sorular, mesela şunun gibi 3 tane soru koyduğunu düşün. Onu bilen birisi direkt 100 alacak. Sonra bir bakacak, sınavda sınıfın yarısı 100 almış. Ama o 100 alanlar arasında da aslında bir dağılım var. Yani bunları çok rahat yaptığı gibi bundan çok daha zor sorular yapabilecek öğrenciler de aslında. Öyle sınavda bir öğrenci hiç sevmezdim. Çünkü yani ben o kadar çalışmışım, her şeyi biliyorum falan. 100 almışım. Bakıyorum herkes 100 almış. Yani onlarla benim farkım ortaya çıkmadı, kötü oldu falan diye. O yüzden yani zor soru da olması gerekiyor bence. Kolay soru olması da gerekiyor. Ki bütün sınıf dağılımını görebilelim.